Welcome back guys to this NPTEL online certification course in molecular rearrangement and reactive intermediates. So I am continuing with the carbocation. So last two classes also I have talked about the various different carbocationic rearrangement, and if you remember I actually end my last class actually talking about the Beckmann rearrangement, and I have shown you some example. In today's class I am going to show you the Beckmann rearrangement, but instead of happening rearrangement something else is going to happen. So let us start the today's class. So in the today's class we are going to cover this important topic. So we are going to talk about the Beckmann fragmentation. So now we are going to talk about that instead of happening the rearrangement, there will be fragmentation going to happen. Then I am going to talk about some of this classical Friedel-Crafts reaction where it's going through formation of a carbocationic intermediate forming a sigma complex. Then I am going to talk about the Fries rearrangement, and then the dienone phenol rearrangement, and some of the exam questions I am going to discuss at the end of the lecture. So at the beginning I am going to start with the place where I left in the last class. So in the last class, if you guys remember that I was talking about Beckmann rearrangement, where the first step is starting from a carbonyl and a hydroxylamine, we are forming a oxime. And if you remember, once you protonate the oxime, then the group which is trans to the hydroxy group participated in 1,2 migration and elimination of water. But now if you see once we start with something like this, so we start with a oxime where one side you have a tarbutol group, one side you have a methyl group, and you can clearly see that your tarbutol group is trans to this OH group. So now first step is the protonation, because this reactions was done in presence of acid. So its first step is the protonation of OH. So the next step is supposed to be the migration of this group which is trans to it going to get migrate, and then the water supposed to eliminate to form this type of nitrogen ion. But the problem is this reaction does not happen. So once this reaction was studied, it actually end up forming something else. So what is happening here, that instead of this migration happen, as the tertiary butyls are very stable, because instead of going for the migration there is this fragmentation happen here. So this carbon and this tarbutol group this bond get fragmented, which generate the more stable the tertiary carbocation, and then the rest of the part which is this part, now you can clearly see there will be a fragmentation happening here, and then as there will be a positive charge here, that means now this bond can push the form this triple bond here and release the water. So there will be a heterolytic cleavage to generate this type of carbocation, and then you end up getting a corresponding nitrile. So instead of formation of the corresponding amide which you have learned in the last class in the Beckmann rearrangement, here we are seeing a Beckmann type of fragmentation happening, where we are getting to a stable carbocation and then corresponding nitrile. Now this carbocation can go for elimination, can go for a E1 elimination to form this olefin, okay, or it can take a nucleophile. So now we are going to try to learn some of this example of this reaction. So here let us start with this example here. So here in this reaction once we start with this particular substrate here, first thing is that you are using the SOCl2 that can convert that to a leaving group. Now what is going to happen, if you have a hydroxy group here on that next carbon, so that is allowing some sort of a migration happening, because the OH is coming back and this double bond is moving to this double bond of the oxime, which end up making this nitrile, and then this lone pair is going to come back to form this carbon compound. So what is happening, instead of the shift which you have learned in the Beckmann, now we are seeing that there is a ring opening happening, and we are isolating the corresponding nitrile, okay, because one of the reason is you are forming a stable carbocation. So that means if you find that in the Beckmann reaction there is a chance that there is a formation of stable carbocation, then the reaction will try to go for fragmentation instead of the desired product. There is one more example happen here. So sometimes the stabilization of carbocation as well as the strain ring opening also leads to Beckmann fragmentation. So that means, as I told you, before also, that when you talk about carbocation, lot of time, you have seen that only the stability of the carbocation is not the factor. Sometimes the ring strain is also another factor. So if you can, release the strain, somehow, then that type of reaction is also getting favorable. So here what is happening, first step is you can see, you can able to, make it activated using this, OH can be converted to corresponding, leaving group here. After reacting with corresponding, benzoyl chloride, then what is happening, as now it's, become a leaving group. So now what is going to happen, it can have a chance for fragmentation. So because once it's getting, fragmented, it is forming a corresponding, a 3 degree carbocation. At the same time, it is actually, releasing the, so there is a, 4 member ring, so that ring strain is also getting released once you convert to here. At the same time, it is forming this nitrile, and after that there will be a E1 elimination going to happen to give to this, corresponding product. So that means you can see here again, there, here there is, 2 important factor. One is the formation of the more stable carbocation, and the second factor is there is a, opening of this ring, so the ring strain is getting released. So let us go for the, next example here. Again, the first things will be formation of this oxime. Once you have a carbonyl compound, first thing is formation of the oxime. So here, instead of getting the, protonation, what is happening, it's converting to corresponding leaving group. So it is getting converted to the corresponding leaving group. Once it is getting, converted to corresponding leaving group, as you know, that now there is a chance of, breaking, because now what is going to happen, it can break either from this side or from this side. But if you see it, if we break from this side, it is going to form the more stable, tertiary carbocation. So that is why the breaking from this side will be, more favorable, and then after that you can see if it is forming a carbocation, it can abstract a proton from here to form this corresponding, olefin with this nitrile group there. Okay, I hope you guys understood this. So now actually there are, more example of this fragmentation. Again, some of this you can find in your practice questions. So now I am going to move to another very important reaction, which is, Friedel-Crafts reaction. So Friedel-Crafts reaction is nothing but that you take a, a aromatic compounds, and then you take a, corresponding alkyl halide or corresponding acyl chloride. In presence of a Lewis acid, it will, so that R group, which is have a positive charge, going to get inserted into the benzene ring. It was discovered by, Charles Friedel and, James Crafts. So it was discovered in 1877, and it is one of the very important, reaction in, organic synthesis. So these reactions actually, goes via electrophilic aromatic substitution. Okay. So generally we are going to talk about, these 2 different type of the reaction, where you have a alkyl chloride and you have a, catalyst, which could be mostly as a, Lewis acid, which give you alkylated benzenes, or it could be acyl chloride with, corresponding, using some Lewis acid, which can give it to the corresponding, acyl benzene. So now, as I said that, this reaction occurs via electrophilic, aromatic substitution. We are going to talk about, some of the elementary step of this reaction, and then the formation of this, important sigma complex. So if you think about the tangential of this reaction, the first thing what is happening, first thing, once this, phenyl ring is reacting with your this sort of, charge species, it is getting to the a species called sigma complex, which is actually is a, de-aromatized species. So there is a de-aromatase happening in the benzene ring, which is actually generating a carbocation here. And so what is happening, so this is a very high energy transition state, because because the benzene ring is actually, losing its aromaticity. So now it is going to form some sort of a intermediate, a carbocationic intermediate here. Okay. So this type of carbocationic intermediate called the, sigma complex. So now after that, what is going to happen, now the, this, proton is getting abstracted, and once this proton is getting abstracted, it is forming to the corresponding product. So that means it is going from the, tangent state to where this proton abstraction is happening, and which is going to the corresponding product. So this is, basic mechanism of a electrophilic aromatic substitution. So moving further, now we are going to try to learn about, the different conditions we are used. For alkyl chloride, we can use, different alkyl chlorides here, or we can use different, allyl or aryl systems. We can use, different acyl chlorides as well of this. So what is happening, as you see that generally if you have electron donating groups, then this reaction will be more preferable compared to if you have a electron withdrawing group, because you are reacting with a electron deficient species. That means the benzene ring, if it is electronically rich, then the reaction will be more favorable. And then people try to use nitrobenzene as a solvent, because as you can see the nitrobenzenes are very electron deficient, so it will not going to take part in the Friedel-Crafts reaction. Now the question arises that if you have a electron donating group or electron withdrawing group, now whatever products you are going to obtain by doing the Friedel-Crafts alkylation or using the Friedel-Crafts acylation. So that can be explained by simple the resonance structures. So the methoxy group have a you can see this group has a plus R effect. So if you try to draw the different resonance structure, you can see it can give electron density more in the ortho and para position. Okay. So you can see it can give electron density more in the ortho and in para position. That means if you want to trap with the electrophile, then it will be more preferable to connect the electrophile in these positions. That means the ortho and in the para positions. But once you go to electron withdrawing group here, now if you try to draw the the resonance structure, you can clearly see you are generating carbocationic character at ortho and para position. That means those are the positions which need to be avoided, because there is already a carbocationic character formation happening, so you cannot bring another carbocation there. That means the meta position, which is the one here, which is going to be the place where the carbocation is can connect it. So that's why you can see for electron withdrawing group, if you try to do Friedel-Crafts reaction, it will almost happen in the meta position. But if you have electron donating group, it happen in the ortho and para position. So now we try to see some of the things here that so one of the other important thing about this, we try to understand what mechanism these reactions happening. Suppose if you are reacting with AlCl3 and this type of chloride. So what it does actually if you have this compound like EtCH2Cl, AlCl3 first activate the chlorine, and at the end what is going to form, it forms some sort of a carbocationic character. So it actually generate a carbocationic character here. Okay. So that means that you can clearly see that if you make a carbocationic which is a tertiary versus a primary versus a secondary, then the reaction rate will be depending on that particular things, that which carbocation will be more stable, because if it is going through a tertiary, then the reaction will be faster compared to a secondary, compared to a primary. And now the problem is, suppose if you do a Friedel-Crafts reaction, Friedel-Crafts alkylation, and you want to stop this reaction in the monoalkylation stage, that means you want to do the first reaction and you want to stop it. But that does not happen. The reaction continuously happen, because once you do the first monoalkylation, now this benzene ring is even more electron rich. So it can go for the next sort of a Friedel-Crafts reaction to give you the mixture. So you end up getting the dialkylation and monoalkylation. So now the question comes that if I want only the monoalkylation product, what are the best approach? The other approach is if you can do acylation. Again, this acylation can be done with AlCl3 and other Lewis acid. So what is happening here, if you try to understand the mechanism here, again it is you have this chlorine here. Now the AlCl3 is activating this. Now this oxygen lone pair now can push the electron to get rid of this chlorine to form. So this is called acylium ion. So it is forming this acylium ion. So now this benzene ring can come and attack here. Okay. Now you can see there, once you form this first acylation product, what is going to happen next? Now what you have done, you put a electron withdrawing group into the benzene ring. If you put a electron withdrawing group, then your tendency to react again is getting decreased. It is not going to. So if you compare them, if you compare this one and this one, then this is more electron rich. That means there is no way this can go for a diacylation. So that way you can stop in the acylation, and after that you can just able to remove this carbonyl group through Clevenson reduction and other reactions to get to the corresponding product. So instead of going for alkylation, you can do acylation and then the reduction of the carbonyl group. Okay. So there are some example here. Start with this example. So this is used for the synthesis of very important compounds here. First thing is going for the Friedel-Crafts reaction. As you can see, there is this ortho and para position which can be go for the Friedel-Crafts. As you see there, if you bring in ortho, there should be a steric effect. So that's why it prefers to go for this para position. And then after this transformations, several transformations is goes to the corresponding product. There is other reactions here which is not from the aromatic ring. So, there is the olefin which is actually reacting with your corresponding acyl bromide. So, you have the acyl bromide and the olefin in the same molecule. Once you activate this with a titanium bromide, which is a Lewis acid, is going to allow this double bond to react here with this, and the bromine will come back and then attached here. As soon as it form a carbocation, the bromine will come back and attached here to form this compound, which can be further converted to the formation of these natural products. Okay. Other rearrangement. So, we have learned about the Friedel curves. Now, there is another important rearrangement from which actually convert the phenolic esters into the hydroxyaryl ketone. So, you start with this phenolic esters, use a Lewis acid, which actually we are going to bring again the the AlCl3 here, and it's end up giving you the the acyl going to get migrated from the ortho or in the para position. So, you end up getting to this ortho and para product. So, this was discovered by the German chemist Carl T Fries, who actually discovered this reaction. So, I am going to talk about the Lewis acid catalyst in the Fries rearrangement, and I am going to talk about some of the anionic Fries rearrangement. So, we are going to talk about also the photo Fries during the radical chemistry. So, here first thing what is happening, once you have this compound, this oxygen is going to bind with this AlCl3 making a positive charge. What is doing after that, this oxygen lone pair now pushing the electron density to form this these particular compounds here and this acylium ion. So, once it is forming the acylium ion, which is very reactive, now you can see about this a Friedel curve type reaction happening, which is taking attacking here, and then after that there is a proton abstraction happening here to form these desired compounds. Okay. So, this is about the Fries rearrangement, and in case of anionic Fries rearrangement, what is happening? We have this type of carbamate group which act as a directing group if you use the organolithium reagent. So, it will form a corresponding lithium here, which you are seeing, and once it is forming the lithium, now the lithium is very much reactive. So, it can go for a intramolecular attack to this amide, and then it will open up the ring, it forms this type of 4-member ring here. After that opening up this this bond of carbon and oxygen, it will end up making this corresponding product. So, what is happening now, this CO NET2 actually moved from this oxygen to the neighboring carbon. Okay. So, this is an example of an anionic Fries rearrangement. And now we are moving further to another important reaction, which is called dienone phenol rearrangement. Okay. This is also done in presence of acid. So, this is a acid catalyzed rearrangement where you start with a dienone, and then it will go to convert to corresponding phenol. And if you look into this, the important changes happen. If you started from dienone, you can see the only thing happened, the R2 moved from this position to this position. So, that is the only change happened, and your dienone actually converted to corresponding phenol. But if you look into this, your molecular weight didn't change at all. Okay. So, this reaction was discovered by Carl von Auer and then Carl Ziegler. So, this was catalyzed by the protic acid. So, now we try to understand the mechanism of this reaction. So, first thing is that once you put a H plus, it is going to protonate this oxygen. Once it is going to protonate, now it is going to double bond getting delocalized to generate a positive charge here. And once you have seen there is a generation of a positive charge. So, this is so now there is a 1-2 shift happening of this methyl group from this position to this position to generate the more stable a tertiary and allylic. So, previously it was a secondary allylic, now it is a tertiary and allylic. Okay. So, after that there will be a proton abstraction which is going to convert you to the corresponding phenol. And so, there is another example here, very similarly this is getting protonated first. Once it is protonating, you are forming a carbocation here. This is allowing this methyl group to migrate to form this carbocation here. After that, you can see there is a proton abstraction to form this corresponding phenol. So, now we are going to see some of the example. So, the problem is that we have learned this in the dienone phenol rearrangement, that there will be always 2 groups here. So, in case of dienone, you have 2 different groups in this position. So, one is going to get migrated. So, again I think you can see clearly that when the migration is happening, the migrating group is carrying some sort of a delta positive charge, which I am telling you from this previous from the Wagner-Marwin to the Pinnacle, in all these different rearrangement, you have seen that there is a formation of some sort of a 3 center 2 electron species, and I am sure very similar things are happening here. So now the thing is, as you see that your migrating group is carrying some sort of a delta positive charge, that means once it is getting migrated, so that means if you have a phenyl versus methyl, the phenyl is going to get migrated. So that's why you have seen here in this reaction phenyl is getting migrated instead of the methyl. And if you have a phenyl and ester, again you can see ester is a electron withdrawing group, but phenyl is a electron stabilizing group. But what we have observed here, we have seen the product where the ester is migrated, not the phenyl. So there is must be something is different. So let's try to understand what is happening. Once you protonate first here, then there will be formation of a carbocation. Now as soon as you have a formation of a carbocation, now the next question is what migrate. Suppose you have a phenyl migration. Once you phenyl migrate, you have to think about also what carbocation is forming. That is also important, because the carbocation which is forming, if it is very much unfavorable, it is next to electron withdrawing group, then there is a very less chance of formation of this carbocation. It will prefer to form this particular carbocation where it will be getting stabilized. So that means that is also another important thing, that in the diene-phenol rearrangement, after the migration, the carbocation also has to be get stabilized. So that's why, because of the phenyl is getting phenyl is stabilizing this carbocation, now the ester is getting migrated to form this product. We can see another example here where you can see there is a methyl group clearly trying to get migrated once you protonate here, because once you protonate, this will make a positive charge that will allow this methyl to migrate to neutralize the charge to get to this product. So here are some of the example of fragmentation. So you can see we have a 2 different hydroxy group here. So it's a very symmetrical molecule. Once it is getting protonated to form a positive charge. Now to avoid the ring strain, there is a tendency to open up. Okay, so that will form this double bond and corresponding aldehyde compounds. Although these alcohols are not in the vicinal position, but still because of the ring strain, it is trying to open up, and it will form this corresponding product. There is another example here. So once you protonate this, you get this OH plus. Now to neutralize this charge, there is a chance of fragmentation. Again, there is a 4-member cyclobutane ring which try to expand to avoid the strain. So this lone pair can attack here, open the ring, and you can able to make, starting from this fused compound, you can make this corresponding 1,4 diketone compounds. So now moving further, we have other example about the fragmentation. Now once this one get protonated, what is going to happen? Once very similar to, so we have learned in this the dienone-phenone rearrangement, that you see once it is getting protonated, it is forming some sort of a carbocationic character. So if you forming a carbocationic character here, now to neutralize the charge, what is going to happen? There is I think we have already talked about this type of 1,2 shift. So that type of 1,2 shift going to happen to form this carbocation here. So again I think this will be a more stable carbocation here, which can take this Cl minus to form this corresponding product. Okay, because you can see, so this carbocation is formation happening in this position where there is a ring fusion, so it will be very difficult to get a planarity. So that's why it will automatically go for this 1,2 shift to form this product. There is another example here. First thing you can see, you can have a protonation of this OH group forming a carbocation. Once you form a carbocation and once you have a methoxy group in this position, so what is going to allow, it is going to give the lone pair back, and then it is going to form this double bond, and then this can get to the corresponding, now once it is forming this, now this is allowing for a intramolecular cyclisation reaction. So now this double bond can double bond electron density can be transferred here to form this type of compounds. This is going to form a tertiary carbocation which can react with this formic acid to form this corresponding product. Okay. We have another example of a ring fragmentation where you have a NN dimethyl group here and a OTS group here. So there is a so as I said previously you have seen an example where you have a OME group here, and then after the 1 carbon you have a OH group. So that was allowing you to do a lot of this chemistry. So once you have a carbocation here, after the OH elimination, this can allow to migrate. Now here we have a NME2 group, which is very similarly what is happening. Once this tosyl is ready to leave, now this nitrogen can give the electron density to cleave this bond, and as you can see also this is a sigma star here getting electron density from this corresponding sigma bond. So they are anti-periplanar. As I said before, once they will be anti-periplanar, they can give electron density to form this. From there it can, you can see now once you get the corresponding water, it can cleave here to form this corresponding aldehyde. We know that. It very similar thing happening now if you change the position. Now if you have, instead of having OTS in the equatorial, now if in the axial position. If it is the axial position, then as I said, there is a CH group which is going to be anti-periplanar. So that will allow to after this hydride here to form these corresponding compounds. So now I am going to talk about some of the questions here. GATE in 2012, you can see this question here. So this is a question about the Bergman rearrangement. You can clearly see we are giving the oxime first. So we are giving the hydroxylamine to form the oxime, and then there is paratoluene sulfurine chloride here. So what is going to happen here? You can now try to think about for a moment that what type of reaction going to happen. First thing will be formation of the oxime here, and then you guys know that once the oxime is going to form here, that will go for once you form a oxime here, what is going to happen? That will go for this 1,2 shift. So that will form oxime, then it is going to get protonated, then there will be a 1,2 shift going to happen, which will end up forming you. So then after the 1,2 shift, there will be this there will be the intermediate going to form, and where there will be water going to get attacked to form this corresponding product. So you will end up getting a amide. There is another question here which came in the net, that if you treat with acetyl chloride, so just now I cover it in the discussion, that you will form a carbocation. So there will be again a Bergman fragmentation going to happen, which going to convert to the corresponding olefin, and then it will going to convert to the corresponding nitrile. There is one more question from CSR 2016. So if you take this compound and then take give a H plus, what is going to happen? As soon as you put a H plus, as you can see, so there is a possibility after getting for the protonation, so this bond can going to break and expand here to open up the epoxide to form this type of 4-member carbocation here, which can able to, so the oxygen lone pair can stabilize it to form this corresponding product. So you can see the B will be the right answer here. So now we have another example here. If you take this compound and then put H plus, what is going to happen? So this is came in the net 2017. So here what is going to happen? First step, once you get it H plus here, again you can see the first thing is going to happen is there is a ring expansion to neutralize it. So you end up making some sort of a species here. So there will be carbocation here, and as you can see that is again getting to this in the bridgehead position. So that is not going to be stabilized more. So this bond going to break and move here to neutralize the charge to make a carbocation next to the oxygen, which can give the lone pair to form this corresponding product. Okay, you can practice this question. I think that will help you a lot in the exam. So in this question, I think we have to first you have to understand about this question, that what exactly happening here. So we are talking about there is a carbon bromine bond, so we give a H plus. So what type of reaction this could be? So this is a tertiary carbon bromine bond. Okay, so definitely we are talking about a SN1 type reaction. So now think about it, that if you are trying to go for a SN1 reaction, what will be your product? We all know that if it is going for SN1 reaction, then the first step will be formation of the ionization of the carbon bromine bond, and then formation of the carbocation. Okay, so if you form a carbocation, then next thing is going to be where the nucleophile is going to attack. Because if you see all the different products, you see they have very same structure but different stereochemistry. That means it is trying to guide you that there must be the OH must be come from a particular phase. To understand that, you have to kind of draw the structure of it. So if you can able to draw the structure of it using this cyclohexane, then you can able to find out where the carbocation formation is happening. So if there is ionization of this carbon bromine bond to form a carbocation here, now you can see that your nucleophile, if you try to approach from this phase, is going to get hindered because of these three CH bond here. So these three CH bond in axial position, that is not going to allow you. So instead of that, the nucleophile will come back from the top phase, and it will end up giving you to the this product. So that means you should also practice the stereochemistry. That is also going to guide you with some of the problems. Today's class I try to cover you the Bergman fragmentation, the Friedel-Crafts reaction, Fry's rearrangement, the dienone phenol rearrangement, and then the the ring opening and using the carbocation. And also we talk about some of the problem in the net and gate. I'm sure I'm going to provide in the mode problem during the practice questions. I'm going to provide you the mode problem in the practice questions, and with that I think you can go through the reference. And thank you all for coming to the class, and I'm looking forward to see you guys in the next class.